Roughly half of us will break a bone at some point in our lives. Whether it's a slip on the ice or a tightrope accident, the force to snap a long bone results from an intense, sudden impact. We often treat our skeletons as dead, rock-like pillars supporting our weight. But bone is actually active tissue, housing its own specialized cells and a constant supply of energy. Look at this cross-section of a healthy long bone. You have a rigid outer structure made of a protein matrix reinforced with minerals like calcium. Inside that stiff exterior is spongy marrow full of stem cells, and weaving through the entire structure is a network of blood vessels and nerves. When that rigid matrix snaps, the blood vessels inside it rupture, causing internal bleeding and inflammation. At the same moment, the nerves encased in the hard tissue relay the searing pain signal associated with the break. This fracture represents the localized collapse of a microscopic, living ecosystem. To manage the damage, the body has to initiate a specific biological response to stabilize the site and begin the healing process. The first step in this response is the inflammatory phase. Over the next week, the body has to clear out the biological wreckage before any new construction can begin. It floods the injury site with immune cells to remove damaged tissue and signaling molecules to recruit repair cells. These draw stem cells to the site, differentiating them into specialized chondrocytes. As we see here, chondrocytes use clotted blood as a scaffold to rapidly build a temporary cartilage callus. It grows quickly, but it's much weaker than actual bone, unable to support regular human movement or weight. This biological triage bridges the gap to prevent the fracture from worsening. To return the skeleton to full strength, the body has to transition into a second, slower phase of heavy construction. Over the following weeks, that temporary cartilage patch must be replaced by a rigid, permanent foundation. Specialized bone-building cells called osteoblasts arrive. They systematically swap out the soft cartilage, replacing it with a dense, rigid structure known as a bony callus. This internal construction timeline is sensitive. It can be delayed by a poor diet, a lack of rest, or a messy splintered break. If the bone fragments are significantly displaced, surgeons have to step in. They manually put the pieces back in place, using metal pins, plates, or screws to hold the bone in correct alignment. Whether the pieces are held in place by biological cells or surgical steel, the goal is rigid alignment. Once the structure is stable, the final perfecting stage of healing can begin. The final stage is the remodeling phase, a process that stretches over several months after the bony callus is fully formed. During this time, a different type of cell eats away at the excess bony callus, while osteoblasts lay down refined new tissue. This eventually smooths out the fracture site, often leaving the bone just as strong as it was before. Look at this side-by-side comparison. The cellular mechanics used to heal a shattered bone are actually happening inside you all the time. A fracture just forces these cells to work at an accelerated rate. Even when they aren't healing, bones are constantly remodeling. They adjust their own density and strength in direct response to the amount of physical force they are typically under. As we age, bone density tends to decrease, which is why older populations are statistically more likely to suffer the types of fractures we looked at earlier. We can influence this process through physical activity. Exercises like walking, running, and weightlifting all apply force to the skeleton, which stimulates the bone-building cells to grow a denser, more resilient matrix. We are the active architects of our own internal foundations. By intentionally subjecting our bones to healthy stress today, we fortify them against the impacts of tomorrow.